Activity 5. Light and Color Theory in 3D Environments. In 3D environments, light and color theory play crucial roles in creating realistic and visually appealing scenes. Understanding how light interacts with surfaces and how colors are perceived is essential for achieving lifelike rendering and accurate representation of objects. Here's an overview of light and color theory in the context of 3D environments. Light sources. In 3D environments, light sources emit light rays that illuminate objects within the scene. There are different types of light sources, including point lights, directional lights, spotlights, and area lights. Each type of light source has its unique characteristics and such intensity, directionality, and color. Lighting models. Lighting models simulate how light interacts with surfaces and affects their appearance. This model takes into account factors such as light direction, surface orientation, material properties, and shadows. Common lighting models include Phong, Green Phong, and physically based rendering models. Materials and shading. Materials in 3D environments have properties that determine how they interact with light. These properties include diffuse reflection, specular reflection, ambient reflection, and roughness and transparency. Shading algorithms calculate the color and brightness of each pixel on a surface based on its material properties and lighting conditions. Color representation. Colors in 3D environments are represented using various color spaces such as RGB, red, green, and blue, CMYK, cyan, magenta, yellow, black, and HSV or HSB, hue, saturation, value, and brightness. Different rendering engines and software tools may use different color spaces for internal calculations and display purposes. Color perception. Human perception of color is influenced by factors such as light intensity, surface reflectance, viewing angle, and surrounding environment. Understanding color theory, including concepts like hue, saturation, and brightness, helps artists and designers create visually appealing and harmonious color schemes. Global illumination. Global illumination techniques simulate the indirect lighting effects caused by light bouncing off surface in the environment. This includes effects such as diffuse interreflection, specular reflection, and caustics. Global illumination algorithms such as Radionicity and ray tracing improve the realism of rendered images by accounting for the complex interactions of light in the scene. HDR imaging. High dynamic range imaging techniques capture and represent a wide range of light intensities in 3D environments. HDR images contain more color and brightness information than standard images, allowing for more realistic rendering of scenes with bright highlights and deep shadows. By mastering light color theory in 3D environments, artists and designers can create stunning visual experience that accurately depict the real world or convey the artistic expression. Shading models for realistic textures and shadows. Shading models are essential for creating realistic textures and shadows in 3D environments. These models simulate how light interacts with surface and how shadows are cast, resulting in visually convincing renderings. Here are some shading models commonly used for achieving realistic textures and shadows. Lambertian shading. Lambertian shading, also known as diffuse shading, simulates the matte appearance of surface that evenly scatter light in all directions. It is based on Lambert's cosine law, which states that that the intensity of light reflected from a surface is proportional to the cosine of the angle between the incoming light direction and the surface normal. Lambertian shading is effective for representing materials like matte paint, fabric, and rough surfaces. Pong shading. Pong shading is a specular reflection model that simulates the glossy appearance of surface that reflect light primarily in a specific direction. It combines diffuse and specular components that achieve a more realistic representation of materials with both matte and shiny properties. Pong shading calculates the specular reflection using the Pong reflection model, which takes into account the viewer's direction, light direction, and surface normal. Blind Pong shading. Blind Pong shading is a variation of Pong shading that uses an alternative method for calculating specular reflection. Instead of computing the reflection vector directly, it interpolates the surface normal across the polygon and calculates the specular reflection using the half-wave vector between the view direction and the light direction. Blind Pong shading is computationally less expensive than traditional Pong shading and produces smoother highlights. Physically based rendering. Physically based rendering is an advanced shading model that aims to simulate the physical properties of real-world materials accurately. PBR models use the mathematical equations based on principles of physics such as Fresnel equations for reflection and transmission, microfacet theory for specular reflection, and energy conservation principles. PBR shaders incorporate parameters such as roughness, metallic, and specular intensity to accurately represent a wide range of materials, including metals, plastics, glass, and skin. Shadow mapping. Shadow mapping is a technique used to simulate shadows cast by objects in a scene. It involves rendering the scene from the perspective of the light source and storing depth information in a texture called the shadow map. During the final rendering pass, the shadow map is used to determine whether a point on a surface is in shadow or illuminated by the light source. Shadow mapping can produce soft shadows by applying filtering techniques to the shadow map. Ray tracing. Ray tracing is a rendering technique that simulates the behavior of a light rays as they interact with surfaces in a scene. Ray tracing accurately calculates reflections, refractions, shadows, and indirect lighting effects, resulting in highly realistic renderings. Ray tracing algorithms trace rays of light from the camera through each pixel and simulate their interactions with objects in the scene, considering factors such as material properties, light sources, and occlusions. Ray tracing can produce physically accurate shadows with soft edges, realistic reflections, and refractions, making it suitable for creating high-fidelity visualizations of scenes with complex lighting. These shading models and techniques provide artists and designers with powerful tools for achieving realistic textures and shadows in 3D environments. By understanding the principles behind these models and applying them effectively, you can create immersive and visually stunning renderings that closely resemble real-world scenes. Lighting techniques, point lights, spotlights, etc. Lighting techniques play a critical role in creating realistic and visually compelling 3D environments. Different types of lights such as point lights, spotlights, and area lights offer versatile options for illuminating scenes and controlling the mood and atmosphere. Here's an overview of common lighting techniques used in 3D environments. Point lights. Point lights emit light in all directions from a single point in space, similar to a light bulb. They are often used to simulate omnidirectional light sources such as lamps, light fixtures, and candles. Point lights provide soft, uniform illumination, and are suitable for general scene lighting. Directional lights. Directional lights emit parallel light rays in a specific direction, simulating distant light sources such as the sun or moon. Unlike point lights and spotlights, directional lights have no position in space and illuminate the entire scene uniformly from distant source. Directional lights are often used as the primary light source in outdoor environments and can create realistic daylighting effects, including shadows that appear parallel. Area lights. Area lights are two-dimensional light sources that emit light from a surface rather than a single point. They can have various shapes such as rectangles, circles, or custom shapes, and emit soft diffuse light across the surface area. Area lights produce realistic soft shadows and subtle lighting gradients, making them ideal for simulating natural lighting conditions, such as window lighting or overhead fixtures. Environment lighting. Environment lighting techniques such as image-based lighting and ambient occlusion capture and utilize lighting information from the surrounding environment to illuminate scenes. IBL uses high dynamic range images or panoramic images to provide realistic lighting and reflections based on the environment's lighting conditions. Ambient occlusions approximate the occlusion of light caused by nearby surfaces, resulting in a soft direction lighting effects and enhanced visual depth. Emissive materials. Emissive materials are surfaces that emit light themselves rather than reflecting the light from external sources. They can be used to simulate self-illuminated objects, such as glowing signs, neon lights, or emissive textures. Emissive materials add vibrant accents to scenes and can enhance the overall lighting ambience. By leveraging these lighting techniques effectively, artists and designers can create dynamic, immersive, and visually stunning 3D environments that evoke specific moods, convey narratives, and engage viewers. Each type of light offers unique properties and characteristics that can be combined and adjusted to achieve desired lighting effects and enhance the overall visual quality of the scenes. Thank you so much.